Hello and welcome again to my Physics Online video lecture series. Today's video I'm going to be talking about energy conservation. So at this point you should recall kind of where we've been so far in this series of discussions about energy. First we have the definition for work. So work was defined as force dot displacement. Second, so this was work. Second, we have kinetic energy, which we could use a capital K, and that is 1/2 mv squared. This is kinetic energy, specifically translational kinetic energy. There is also a rotational kinetic energy that we will discuss later. And then the third item to recall is that we have defined potential energy within our system as potential to do work. So change in potential energy and therefore the change in potential energy, or the negative of the change of the potential energy within a system, is the work done by some conservative force. Now a distinction maybe needs to be drawn between what we've written for step 1, the work done by a force in general, and what I've written for point number 3, the work done by a conservative force. This is how much work any given force could do. We also defined it in terms of the net amount of work done, but if every force within your system is conservative, then it follows that all work being done by these forces somehow gets translated into potential energy and maybe kinetic energy within the system. However, there can be non-conservative forces which also do work within the system. So we can basically put these 3 points together to define what's essentially the total mechanical energy within a system. So we might say E mechanical, or E sub m for mechanical, which is potential energy plus kinetic energy in the system. And as long as there is no work done, this quantity should remain constant, or no work done by non-conservative forces in the system. This quantity remains constant. So we could essentially say that delta mechanical energy is equal to work by non-conservative forces. Put differently, we have in some sense our law for conservation of energy. And that law can be written several ways that all basically say the same thing. One version is that the initial kinetic energy plus the initial potential energy for the system plus any work done by non-conservative forces is equal to the kinetic energy final for the system plus the potential energy final for the system. Now again, this is conservation of mechanical energy only. We're not trying to take into account things like heat or chemical reactions or anything like that. But you could in principle include those things within this equation and sort of broaden its scope. For our purposes, this is sufficient. This is your conservation of energy equation. The work being done by non-conservative forces essentially can either add to the total energy in the system. That would be, for example, an object which is initially at rest and you walk over and start pushing the object. You're doing work on it, and that's not really conservative. It could also be an object that's sliding down a ramp, let's say, and there's friction present. In this case, friction is working against the object as it slides down the ramp, and that's also not conservative, and that would be taking energy away from the system. So the sign of this thing, this plus or minus, this is plus if we're adding energy to the system. So if we're adding mechanical energy minus if we're removing mechanical energy. And that's it. That is our law of energy conservation. And this is a law that is very broadly applicable. Essentially, you may have a system in which energy is not being conserved because you have an outside force that is acting on the system. But if you broaden your system to include all sources of outside forces, then classically energy has to be conserved. And if you broaden your definition from mechanical energy to include things like nuclear and chemical and etc., heat, then your energy for the whole system and its environment must collectively be conserved. But you kind of have to define your system of interest, and that is essentially a little bit of an art and a little bit of a science, in as much as the larger your system is and the more things you account for, the better this law will be followed, but also the more difficult it is to actually account for everything. And so we usually, at least in this introductory course, apply this to mechanical energy only and to limited systems. And it works quite well within those contexts. For example, let's consider an object on a ramp. Okay, so I have a ramp, and the ramp need not be a true inclined plane ramp. It could be a curly ramp like this. Maybe it's a frictionless ramp. All right, so I have this object here. I have the bottom of the ramp down here, and I want to know how fast the object is going to go here. So V initial is 0, V final at this bottom is unknown. And what we do is we figure out essentially how much potential energy change is there. So for example, this may have a mass m, this might be a height h. And basically we just say initially we have m times g times h plus 0 kinetic energy. And finally we have 1/2 mv final squared plus 0 potential energy. And so this lets us find what our final speed is by basically solving this equation. Essentially divide both sides by 1/2 m, and what you end up with is 2gh. And notice that that is going to be the same whether the ramp is like this or whether the ramp takes some more twists and turns. So same speed for both ramps, same speed at bottom. Note that same speed at bottom does not necessarily mean it took the same time to get there. So same speed here does not necessarily mean that it took the same amount of time to get here from this initial starting point. So energy conservation in some sense means we care a lot about the starting and ending points and not a lot about how it got from one to the other. Now there is again a caveat. This was a frictionless ramp, so this is frictionless. That means no work is being done by friction. If there is friction and that has to be accounted for, then a different amount of work may be done by one ramp than by the other, and the result is that you're going to have different speeds when you get to the bottom because you've removed different amounts of energy. We can complicate our example somewhat. So here's another conceptual example. Maybe you have a ramp that does this kind of thing again, and then at the end of the ramp you happen to have a little platform, and the platform has a spring attached to it. Okay, so the spring can be compressed. It's an ideal spring. And again, we start with the object up here, but maybe this time it has V initial is not 0. So it's initially moving. How much does the spring at the bottom compress? Okay, so what we have is an initial condition. So initially you have kinetic plus potential, which is 1/2 mv squared initial plus mgh. Again, we're taking this distance right here to be the height h. Okay. Finally, what you have is kinetic plus potential. And how far does this compress? Well, it stops compressing when the speed is 0. So h equals 0, v equals 0. But your potential energy is 1/2 k times whatever your compression is, kx squared. And so you can set these two things equal to each other. You get 1/2 mv initial squared plus mgh is 1/2 kx squared. And that means that the final compression must be mv initial squared plus 2 mgh all divided by k square rooted. And again, we did this very easily without having to figure out intermediate things like what's the acceleration, what's the force on this, what's the acceleration at each point, therefore what's the speed when it gets here, therefore how much force is needed and what acceleration to bring it to a stop, and so on. This was like 3 lines to a solution of what would, with just a forces analysis, be a very complicated problem, and in fact not a problem you could really solve in an algebra-based class with this wiggly ramp. You could do it with a straight ramp, but you can't do it with the wiggly ramp. Okay, so that's all I'm going to do in this little video introducing this subject. So hopefully you've learned something from it. Thanks for watching.